Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck as we're continuing our journey through mathematics. Today, our discussion is going to be about ellipses. And a lot of people, when they hear the word ellipse, what they think is something of an oval shape. So, is that true? Well, yes, to a certain degree. But one of our objectives for today is to actually understand what that ellipse really represents. And then we're going to analyze them on a coordinate plane. Specifically, this video is going to talk about what happens when the ellipse is at the origin. And then we're going to do some applications. And usually the applications, we tend to put them at the origin just because it makes the calculations a little bit easier for us. So let's get into what actually an ellipse is. So my oval, very, very bad drawing of ovals, which is why I'm going to be using and utilizing GeoGebra today to help with a much nicer drawing. But so an ellipse, it's an oval, yes and no. It is an oval, but it's not just any oval. It's an oval that if you have 2 points, which we're going to call foci, you can either call them foci or foci. Both are acceptable. But if you have 2 points, the ellipse is really the sum of the distance. How about the collection of all points? So let's make this random point P. So if I take the distance from each focus, let's call that D1 and that one D2. If we add those two distances together, we end up with some value. Well, what happens if that point was over here? That D1 plus D2 will give us the exact same value. So no matter what, D1 plus D2 ends up giving the exact same value. Let's go into a little bit more of the anatomy of this ellipse. So if the ellipse is a collection of all points whose sum of distances are the same, if we draw a line through the foci, what will happen is we get what we call the major axis. A lot of times we refer to the major axis, that major axis should continue on forever, but we don't care as much about all the stuff on the sides here. What we care about is what is and what we call the length of the major axis. So the length of the major axis is that distance across. That length will have a distance of 2a, and I know you don't understand what a represents yet, and that's okay. We're going to define that as 2a. What a is the distance from the center of the ellipse to each vertex. So that value is a. Now, as you can see, this picture is starting to get really convoluted already. So let me erase and let me change the size of the eraser so I'm not erasing everything. So let me erase those pieces of information. So what you can see is that length right there is a. Each length is a from the center to each vertex. Now, that center is actually the midpoint, as you can see. I have defined here on the side that center is the midpoint, which is how I know that both sides are A. We also have a minor axis, and that minor axis is created by taking a perpendicular. This is kind of like a nice fun geometry review. But if we take a perpendicular to the major axis through the center, we get what we call the minor axis. Now, once again, and I'm going to go ahead and draw it so that that minor axis really extends from, in this case, the top to the bottom of the ellipse. So we know that's perpendicular. And what we're going to do is we're going to call that distance B. And again, I know A and B don't seem to have a whole lot of relevance right now, but they will, and you'll see that as we build our equation. The length of the minor axis then is 2b. This is where I usually joke 2b or not to be. That is the question. Okay, bad math jokes. Now, some books call these vertices as well. So some books consider this, or each ellipse to have 4 vertices. Some books actually call these covertices. Our book just actually ignores them, but they're very helpful, especially because that b value is going to be very, very important. So what I want to show you, though, is I want to show you a little bit about an ellipse that you guys are familiar with already, and that ellipse is going to be the circle. Now, if you remember, I defined that ellipse to be the distance from one point to each focus. Now, what I've established is the focus length is 0. So if I move this focus length out, what we're going to do is we are going to create an ellipse. So the closer the foci get to the vertices, the much wider that ellipse is. So I want you to focus on this distance sum right here. And as I move this point generically around, that distance sum is going to remain the same. And that's how we know that the ellipse is actually being created. There's a lot of geometry that goes into this. And I encourage you, if you want to explore and play, I do have a link on my Canvas page. But I also, if you look at GeoGebra and just go search for ellipses, one of these will come up. So if I change the major length, and once again, if I change my focus length so that it gets closer and closer to that major length or the major axis length, now once again, you'll see that it gets wider and wider. Now, these ellipses don't have to be horizontal. We're going to talk about vertically oriented ellipses as well. But you know, the limitation of, there's so much that goes into these, but the limitation is, you know, how much you want to show about each one of the graphs. You know, what's the focus? You know, pardon the pun on that one. Now, a lot of students at this point ask, well, what happens if we want to extend that focus length so that's bigger than the major axis, which is a very valuable question. So what we have right here is we have a circle, which focus length is 0. We have an ellipse where that focus length is somewhere between 0 and A. And then, interesting thing happens. What happens if these are the exact same lengths? What we see on this graph is just a line. But interestingly enough, this is actually a parabola, which is what we discussed in the previous videos. So really, the idea behind conic sections is this focus length does tell us everything. Really, it's the ratio of the focus length and the major length that tells us what kind of conic we really have. So if our focus length is 0, then we have a circle. If our focus length, which we're going to call C, by the way, if that C value is less than A, we have an ellipse. If that C value equals A, I know we can't see the parabola, but and I kind of jumped the gun, where if that C value is greater than A, that's when we have our hyperbola. So really, in this one application, or this one applet, we could see all the different conic sections. I know the parabola is very, very hard to see because we're looking at it from like a side orientation. But our emphasis today is going to be on this ellipse. So let me go back to the actual note screen. So this focus length, I referenced it as I was on the other page. This focus length is actually C. So we do have a relationship between A, B, and C. For an ellipse, it is not A squared plus B squared equals C squared. It is not that happy Pythagorean theorem. What it is that B squared plus C squared will equal A squared. And this is for an ellipse only. And again, we're identifying what these variables are at the moment. Let's see how they actually go into play. So if we were in a normal classroom, what I would do is I would actually go through this derivation with you guys. Since we're not, I'm gonna have the math up here for us. Now remember, this ellipse is created by having those two distances be the exact same value, which I did say was 2a. And then if we use distance formula in this step and going through the math, distance formula, if we bring this over to the other side, square it, which means we're going to FOIL it out, do a lot of beautiful math down here. We end up with this equation right here. And this is where it's very, very important for us to know this b squared plus c squared equals a squared, because then we're able to simplify that expression into the a squared minus c squared does become the b squared. And then it turns into this massively beautiful equation that looks like this. So why this is so cool is, in my opinion, is if you remember that x equals r cosine theta. So if x equals r cosine theta, this r, rather than call r, this is going to be our horizontal radius, which I'm going to call a in this graph. And if y equals r sine theta, or y equals b sine theta, because b is our vertical radius. So I call a the horizontal radius. So the horizontal radius, and b is the vertical radius. then if we solve for cosine of theta is x over a, sine of theta is y over b, and if you look, we get cosine squared theta plus sine squared theta equals 1. So really, this kind of goes back to, if you look at our circles, our circle is what happens if the radius is the same, cosine squared plus sine squared equals 1. With an ellipse, this Pythagorean theorem actually sort of works on a trigonometric level. And that's really the blend of, and why we have this, when we talk about a lot of this in trigonometry, that we could see this blending of all the trig values that we know and the trigonometry that we learned right at the very beginning. So without further ado, what does this mean? How do I actually work with this? And to actually work with this, I know I kind of talked about what I consider the anatomy of the ellipse, which that anatomy is so important to understand how it's created. Now, how do we actually graph them? And we're going to go through as more of like an introductory level to graphing these ellipses. Now, I do have a lot of information in this table right here, but if you remember from the work that we did with parabolas, I don't necessarily like to just have these written as a formula. If you see this, do it this way. It's more of the ideas. For instance, if I take a look at this equation in example number 1. So in example number 1, this 16 represents a horizontal radius, and this 25, let me go ahead and actually highlight and use different colors. So that 16 represents a horizontal radius, where this 25 is going to represent a vertical radius. Now those radii are going to be coming off of a center, and because we are not seeing, and I have this up here, because we're not seeing the x minus h squared and the y minus k squared, that means that my center is going to be at 0, 0. So my center is going to be at 0, 0. So let me go ahead and plot my center. And this is where I'm going to utilize my horizontal radius. If you remember, my horizontal radius is 16. So if I go 4 units over to the side, so 4 units horizontally, then let me go ahead and erase those. If I go 4 units horizontally, I get 2 endpoints, or I get my horizontal distance across. And if I go the square root of that, 25, so 5 units vertically, we end up here and here. That's where we're going to get our ellipse. So let me go ahead and use red to finish off this. Now, this is where understanding that relationship, ooh, that part was very badly drawn. Understanding the relationship between A, B, and C is very, very essential as well. Still horribly drawn, I'm sorry, guys. What is A, what is B, what is C? Officially, we don't, if you're looking at this from a geometric level, A, B, and C don't necessarily matter as much. If you're looking at this on an algebraic level or kind of building this graph, they matter a lot. So this is where, let's go ahead and take a look at the table that I have up top. If you notice on this one, if your major axis is parallel to the x-axis, or in this case is the x-axis, A goes with the x. If you're parallel to the y-axis, A goes with the y. What does this mean? If we go back to what I discussed up here, the major axis is always considered to be the A value. The minor axis is always considered to be the B value. So here, this was a horizontal orientation, which is why A was horizontal. In this case, this is more of a vertical orientation. So this distance right here, this vertical distance is A, this horizontal distance is B. So A is 5 and B is 4. Now, why do we care about the major axis being the longer one? Well, if you look at an ellipse, it's really a flattened circle. So knowing which direction we flatten gives us our major axis. And more importantly, I had a little bit of technological issues. More importantly, if we look at this as a Pythagorean theorem, if A is smaller than B, then C is an imaginary number and we have no foci or foci. So for an ellipse, it's essential that A is going to be bigger than B. So let's go ahead and put that for an ellipse. A has to be greater than B, or else C is going to be imaginary. And this is the perfect opportunity to bring back this idea of what is called eccentricity or eccentricity or eccentricity. I've heard all these different pronunciations. What I hear most often is eccentricity, so I'm going to call it eccentricity. It's this ratio of C over A, which if you go back to the graph that I have here, right now C, which is our focus length, is 0. A, let's actually make this 5, just so that we have some nice numbers. So our eccentricity of this is 0 over 5, which makes a circle. For the ellipse, our eccentricity is some number over 5. And if you notice, that number is smaller than 5. So our eccentricity between 0 and 1 will give us the ellipse. Our eccentricity of 1 gives us a parabola, if I can get that. And then our eccentricity above 1, meaning our foci length is bigger than, our C is bigger than our A, we're going to get a hyperbola. So circles, once again, eccentricity is 0. Ellipses, the eccentricity is between 0 and 1. Parabola, eccentricity is 1. And then hyperbola, eccentricity is above 1. Now, this course is not going to get into the eccentricity as much, but where are ellipses used in real life? The planetary motion. So if you remember, a lot of our conic sections revolve from, pardon the pun on that one, about our like a lot of the motion of the planets in astronomy. So that's where this was really developed and built on. Each planet has its own eccentricity, meaning each planet has its own orbit. None of the orbits are circular, they're all elliptical. And fun fact, the sun is one of the foci of those orbits. So, which shows when you talk about, why do we care about an ellipse, the sum of the distances being the same? When you're talking about two forces interrelating with each other, it's really when those forces have to stay stabilized, and what it does is it creates a elliptical path. So there are a lot of cool things that come out of conic sections. So anyway, back to our problem at hand. So we've graphed our ellipse, and again, graphing the ellipses is very, very easy from the equation. We check out our horizontal radius, our vertical radius, and we plot them. Now, where are the foci? Let's go ahead and erase that. Where are the foci? So C squared is going to be, let's look back up here, just as a reference. How about B squared is A squared minus C squared? So if we rewrite it, C squared is A squared minus B squared. So definitely not Pythagorean theorem like. So C squared is A squared minus B squared. So C squared is 5 squared minus 4 squared. 25 minus 16 gives us 9. So C squared is 9, which means C ends up being 3. So for this problem is very nice. Now, if you remember, our major axis, in this case, was vertical. So if we go 3 units up, there's a focus. 3 units down, we have our focus. All right, now let's give the coordinates of the vertices. Since this is a vertical ellipse, the coordinates are going to be 0 plus or minus our A value, which is 5. Our foci, 0 plus or minus our C value, which is 3. So we can look at the table. Once again, I'm having a little bit of technological issues. So we can look at that, and you can use this information. It's all valid, it all works, but I prefer to look at it on a geometrical level just because it makes more sense or it's a lot easier to come up with all of our values than just memorizing these formulas. So on example number 2, let's choose a different color for this one. On example number 2, if you notice, this is not written in the form that I'm very familiar with. And that very familiar with is, in this case, x squared over a squared plus y squared over b squared equals 1, or x squared over b squared plus y squared over a squared equals 1. So I really need to have one of those two forms, which that is our prompt that all of these are going to equal 1. So let's go ahead and divide everything by 144. And if we divide by 144, we will get x squared over 36, because 4 goes into 144 36 times, plus y squared over, how many times does 9 go into 144? That would be 16 equals 1. So this tells us, this 36 tells us our horizontal radius from the center. And quickly, what is our center? I really wish I would have put center here. Actually, let's just go ahead and do it. What is our center? 0, 0. Let's plot that. And now what is our horizontal radius from that center? That 36 indicates that it's 6 units horizontally, which should be right there, right here. And then that 16 will tell us that it's 4 units vertically. I think I went 5 there accidentally. So let's go 4 units vertically. So here is our ellipse. And if you can see, this ellipse has more of a horizontal representation. So since it's horizontal, A goes with the X value. So A is 6 and B is 4. And remember, C squared is going to be A squared minus B squared. So 36 minus 16 gives me 20. So our C is the square root of 20, or 2 times the square root of 5. Now, which is going to be more beneficial, square root of 20, 2 square root of 5? That's going to be up for debate. So what is the square root of 20? Square root of 20 is somewhere between 4 and 5 because it's between the square root of 16 and the square root of 25. So I'm not going to require you to have 100% absolute precise foci on your graph, but somewhere between 4 and 5 would be right here, roughly halfway in between, slightly less than halfway though. So our vertices are going to be plus or minus 6 comma 0, and our foci we will write as plus or minus 2 root 5 comma 0. So hopefully I didn't go through that graph too quickly. But what it comes down to is we need to know x squared over a squared plus y squared over b squared equals 1, or vice versa. So let's actually build the equation from this given information. So if you remember what the work we did with parabolas, I like to go ahead and make a general sketch so I know what's going on. So in this case, we're focusing on that center being the origin. And what's nice about that is immediately I know that we have x squared plus y squared equals 1. Our goal is just to figure out what goes underneath the x squared and what goes underneath the y squared. So our focus is 8 comma 0. So this graph, my focus is here and my vertex is here. So because the focus and vertex are along the x-axis, this indicates, and it really comes down to, because these are x values, this indicates that this is a horizontal orientation, which means A goes with x and B will go with y. So what is A? If we define A as the distance from center to vertex, that distance is going to be 10. So this is 10 squared. And then our distance from center to focus is C. So we know that A is 10 and C is 8. So how do we figure out what goes underneath the y squared? Well, let's go back to, we know that C squared equals A squared minus B squared. So our goal is to find B now. So rewriting it, B squared will be A squared minus C squared. So B squared is 100 minus 64, which is 36. And really, I want to know what that B squared is anyway, so we could write 36. So x squared over 100 plus y squared over 36 will equal 1. And then that is my equation. For problem number 4, let's go ahead once again, draw it out, and I'm going to change colors just so I could have something a little bit more distinguishing. So now this time I'm not given the center. I can assume it's 0, 0 at the moment, but I'm not given that. So I don't like to make that assumption. I do know that my foci are 7 units above and below, which that tells me a couple different things. Because these are both vertical, I know that, or these both go along with the x-axis, I know both of these are vertical or form a vertical orientation. The foci is our C value, so C equals 7. And then our vertex is going to be 0, 10. We're only given one vertex, but due to the symmetry of the ellipse, we know the other vertex has to be below. So And what does that tell us? That tells us our A value. So, and if you remember, this is where it's going to be important to know that the center is halfway in between the foci, or halfway between the vertices, or halfway between the co-vertices, if you call them that. That's what gives us our center. So indeed, our center is 0, 0. So we could say x squared over plus y squared over equals 1. So what goes with what? So we know that A has to be 10 because that comes from the vertex. If A has to be 10 and it's a vertical orientation, I know that it'll go, the 100 will go with the y squared. And I don't know what my b squared is, but if you remember what we did on the previous problem, b squared is a squared minus c squared. So b squared would be 100 minus 49, which gives me 51. So the equation of this ellipse is x squared over 51 plus y squared over 100 equals 1. One more sample problem like this. So once again, let's draw it out. This time I'm told my foci are plus or minus 9 comma 0. So that tells me two things. That tells me my C value, actually it tells me three things. My C value is 9. It also tells me it's horizontal because the foci go horizontally. And it also tells me my center is halfway in between. So my center, once again, is 0, 0. Since my center is 0, 0, x squared over plus y squared over equals 1. Now I know my C value, and this time I know that my y-intercept is going to be plus or minus 3. So if my center is 0, 0, and my y-intercepts are plus or minus 3, this actually will give me my b value because this is my minor axis that goes through the center. So this 3 is b, and I now know c, I now know b. So if you remember, c squared is a squared minus b squared. Or rewriting it using the c and the b that we know, a squared will equal c squared plus b squared. So a squared is going to equal c squared. 9 squared is 81. B squared is 9. So a squared equals 90. And because my orientation is horizontal, that 90 goes underneath the x squared. And then the y squared should be, or what goes underneath the y squared is b squared, and b squared is 9. So let me write that in one color just to be a little bit better. Okay. A couple applications, and again, a lot of the times we do put our applications so that they are, excuse me, we put our applications so that they are centered at the origin because it makes life a little bit easier. So an arch for a bridge is built in a semi-elliptical shape. So if I have a semi-elliptical shape, let me go ahead and draw it out, and I would do this in a different color. Here's my semi-elliptical shape, and it says a horizontal major axis. The span is 30 feet, so I know this distance is 30 feet, and the top of the arch is 10 feet above the major axis. So the top of the arch is 10 feet. We have a roadway that is also horizontal and is 2 feet above the top of the arch. So here is a roadway that is, this distance is 2 feet above the arch. Our goal is to find the vertical distance from the roadway to the arch 10 feet away from the center of the major, or the center of the semi-ellipse. So if my center is here, the distance from the roadway to the arch, so let me do this in different colors so we can emphasize what's going on. 10 feet away, which would be right here, our goal is to figure out what that distance is. So to do any of this work, our first step is let's build an equation so that we know what's going on. To build an equation, I'm given that this is a horizontal orientation, and it makes sense to make the center at 0, 0, just so the calculations aren't quite as complicated. So x squared over plus y squared over equals 1 is how we're going to start. Horizontally, we know half this distance is 15, so horizontally, that makes that 15 squared. I am told that this distance of 10 is our, in this case, p-value. So 10 squared equals 1. Now, our goal is still, going back to our goal is still to find this distance. What do I know about this distance? I know that this is horizontally 10 units away from the center. I don't know vertically how tall it is. So in the end, once I know vertically how tall that is, I'm going to then add, well, I'm going to use the fact that this overall distance is 12, and I'm going to take 12 minus that y value in order to figure out what that actual distance is. So let's find it. I do know that horizontally I am 10 units away. So 10 squared over 15 squared plus y squared over, let's go ahead and just call it 100 equals 1. So y squared over 100 will equal, and this is where I'm going to write it as 1 minus 100 over 225. So combined together, this is where I could start using the calculator right away, but as you see, I don't have the calculator put up there just yet. So struggle is real, guys. So let's just go ahead and simplify this. This is 200 over 225, or 225 over 225 minus 100 over 225. So 125 over 225. And if I multiply both sides by 100 and take the square root, then I'll say y squared ends up is 125 with 2 zeros, so 12,500 over 225, and then we will take the square root of that. So 12,500 over 225. I do have a calculator off to the side. I wish I had this on the screen right now, my apologies. So 12,500 divided by 225 is 55.5 repeating, and when I take the square root of that, that y value is 7.454. So if that y value is 7.454, then let me go ahead and substitute it back in right here, because once again, we know that this overall distance is 12. If that overall distance is 12, the y value that we found here was 7.454, then that distance is 12 minus 7.454, which I should be able to do this in my mind, but let's use the calculator. So that is 4.546. And what are our units? Feet. So 4.546 feet. Last but not least, we have our whispering gallery. Our whispering gallery is in a semi-elliptical shaped ceiling. Now, I'm not sure how many of you have been to Washington, D.C., and in Washington, D.C., they typically have a whispering gallery there that you have, usually it's a tour guide who stands on one side of the room, and he starts whispering and everybody on the other side of the room can hear it. Because what's happening, and this is really one of the big applications of ellipses, is from your focus, if you put a sound out, what it'll do is it'll bounce and then end up at the other focus. So that's what's happening with our whispering gallery. So where are we at now? We are told in this problem, and I'm going to go ahead and change colors. And in this problem, whispering gallery in Chicago is 47.3 feet long. So this is 47.3 feet long. A person can stand at a focus 3.35 feet away from the wall. So this distance right here is 3.35. And our goal is to figure out how high is the ceiling at its highest point. Now I'm going to assume the entire room's elliptical based off of how this problem is built. Usually in a real life situation, there is an extra height added here. That's not part of our problem, so we're just going to assume this whole thing is elliptical. So if we look at the anatomy of the ellipse, what does this mean? Our goal is to find that b value. So what is a? A is going to be half this distance. So half of 47.3. 47.3 cut in half is 23.65. 23.65. And because I made this a horizontal orientation, this is x squared over 23.65 squared. Our y squared, we don't know vertically what that is, so we're going to call that b squared equals 1. Well, how are we going to find our b squared? Our b squared, if you remember, going back to some of the work we did before, b squared is a squared minus c squared. We happen to know our a, so b squared is 23.65 squared. Now we don't know c. If we don't know c, how are we going to find that? Well, if we know that a is 23.65, and then we know the focus is 3.35 feet away from the wall, so if we subtract 3.35, we're actually going to get what's left over. Let me do this in a different color. So we are going to get, I froze one more time. I love technology. So if we subtract it, we are going to get that C value. So C is 20.3. So 20.3 squared. Now in this case, we actually didn't need the equation, but it's still kind of fun to have anyway. So I'm going to do this work in the calculator. Once again, I really wish that this was on the screen so you could see it, but alas, it is not. 23 squared. So b squared ends up equaling 147.2325. And then when I take the square root of that, b squared is 12.134. And what are our units? Feet. So this is going to end video number 1. It was really long, but we went through the anatomy of the ellipse, and we also went through how to actually graph and analyze those ellipses at the origin. Stay tuned for video number 2, which is away from the origin.